Okay, so I have a question here from one of your colleagues about the format of the exam. The exam is going to be made of arithmetic questions and the multiple choice questions. So you don't need to print off the exam. You can print off, I will update the formula sheet. We got some feedback about the formula sheet to include some of the equations that we did not include, and I'll update that and upload it today after the lecture. If you have any comment about the formula sheet or you think there are some equations that are not listed in that formula sheet, please let me know. If we find that those equations cannot be derived from other equations, so we usually have an equation that covers um, some other equations that you can easily derive from, let me know and I will have a look at it. If I find that those equations need to be added, then I will add it. But you can print off the formula sheet and have it handy with you. You can bring scrap papers with you. Yes, so basically this is what uh, I hope this answers the question for the student who asked. Okay, so today you have also a TA session, a tutorial session. This tutorial session will be made as a review session as well for the material that is covered in quiz number one. Make sure to attend that session. Hopefully, you will benefit from it, and you can also ask questions, ask the TA any question that you want, also related to the material. Any other questions before we start? I will post more information about the quiz, the number of the questions, and all those information once it is finalized. Any other questions? Okay, so yes, it's going to be on Zoom. Okay. So in last lecture, we uh, introduced Thevenin's equivalent circuit and Norton's equivalent circuit. We stopped at an example for calculating the Norton's equivalent circuit. That was example number three, where we wanted to find the Norton's equivalent circuit, and we said I Norton is basically the short circuit right at the output of the question. And we started in this example by, as you can see here, shortening the output of the circuit and calculating this I short circuit. And we said that one of the advantages when it comes to finding the short circuit is this piece of wire that you put at the output of the circuit basically shortens out any parallel component that is connected in parallel with that piece of wire. So here in our case, we had a 6 ohm resistor that was shortened, and the circuit was simplified down to the following. If you recall, we had a current source here that we just removed for simplicity, but this current source has a 4 ampere, and we wrote, we we drew this dashed loop, and we said that this now is my super mesh, and I assigned I1 and I2 to those two meshes that the super mesh is made of, and I wrote the super mesh equation where I uh, write both of them in the same equation, starting with I1 first, that is basically here within this small mesh. And then we said this is minus 15. Then I have a 3 ohm, 3 I1. And then in the same equation, I continue. So this is for the first one. I continued the second one within the same equation, and this is why we call it a super mesh equation, which is basically 3i2. So this one is a 3i2. So I got the super mesh equation, and then I simplified that equation by dividing it by 3. I got this equation. And then I continued and I wrote KCL right at A here to find the relationship between my mesh currents, which are the variables in mesh analysis, and this current source. This is the equation that basically binds both mesh currents with the current source in between here. So here I have, as you can see, I2 is entering A. That's why I wrote it as minus I2. I1 is leaving. That's why I wrote it as positive I1. And then 4 ampere is leaving. I wrote it as positive 4. And then I rearranged this equation. I came up with this equation, I2 minus I1 equals to 4. And then I had equation number 1 and equation number 2, and then I added those two equations. I got rid of I1, then I found I2, which is basically I2 here is the same as the short circuit. We said I2 is the short circuit, and this is the I Norton, and then IN, which is the I Norton, we found to be 4.5 ampere. So right now I found the current for the Norton, which is the current for the short circuit. Now the next step would be is to find our Thevenin. So to find our Norton, which is the same as our Thevenin, so we know here that our Norton equals to our Thevenin as well. So I have two options. Now I found the current. So either I put, I hook up a voltage source right here, but now here my circuit is is only independent sources. So to find our Norton or our Thevenin, I just need to switch off my independent sources. So switching off independent sources while looking from the output of my circuit of my circuit I can find the R Norton. So how does this happen? This is the output of my circuit. So while looking from the output and switching off, so I will be switching off now. I will redraw. And now remember that switching off voltage sources is replacing them with a wire. Switching off current sources, and again independent, only independent currents. Switching off current sources, replacing them with an open circuit. So if I look now at this circuit and I switch off the current and the voltage sources, I will redraw the circuit again. So this is A, B, this is the output. I don't have a load, right? The load in my circuit was already removed, so I don't have a load. So I need our Norton here. So this is 6, 3, open circuit, 3, a wire. Now, can somebody tell me, just by looking at this circuit, what is our Norton? I have 3 resistors that are contributing in our Norton, 6, 3, and 3. Can you tell me what is the relationship between those resistors? Okay, great, Liam. I think you gave me the final answer, and I think your answer is correct. But just to hear, yes, and Prakrit also, that's great. Uh, yeah. Well, that's fine. But can you tell me? I need to hear from a third student. What is the relationship between those 3 resistors? Can somebody tell me?
Sure.
Yeah, go ahead.
So the one of the 3 ohm resistors and the 6 ohm resistor are technically in parallel, but the other third one is in series with those two.
So tell me which ones are in series and which ones are in parallel.
Um, the 3 ohm resistor to the right and the 6 ohm resistor are in parallel. And the other 3 ohm resistor to the left of that is in series with the equivalent of this parallel circuit.
So I don't agree with you, but what I'm going to do, I
Oh,
will now
oh,
add the coloring to the circuit just to make it clearer based on our understanding of the series and parallel. So if
wait,
I am,
sorry.
yeah, go ahead.
No, now I think about the 3 ohm resistors are in series. They make 6, and that's in parallel of the 6 ohm resistor. So
Now that's correct. Now this is correct. Let me put the color here just for those who still did not understand. How did you come up with this? So this is one node, one electrical node in red, and the second electrical node, I will put it in blue, right? And then the orange is in here. So looking at the 3 and the 3, I can see that they're sharing one node and no other components are sharing that node, which means they have the same current going through them, right? Which means that they are in series. So now 3 and the 3 are in series. I will redraw this. So I have here 6, and now the equivalent here is 6. Okay. Using the coloring again, this node is red, and the other one is blue. Now I can see clearly that the 6 and the second 6 resistors, they're sharing both nodes, which means that they are in parallel. So our Norton here is indeed 6 times 6 divided by 6 plus 6, and R Norton is 3 ohm. So this is how we found the R Norton, which is the same as the R Thevenin for that circuit. And as you can see, it's a bit easier when you have only independent sources. You just need to switch off those independent sources and look at the output, calculate R Norton or R Thevenin looking from the output. Now, if you have dependent sources, then you cannot do that straightforward procedure by switching off only. You have to you have to have a second and something else different. You have to either add a voltage or a current source at the output, or you can still look at the general approach, which is calculating the open circuit at the output and calculating the short circuit at the output. Then R Thevenin and R Norton would be basically the ratio between the V open circuit to I short circuit. So this is a second approach that we talked about, and we said that we will see it. Now here we need to find the Norton's equivalent circuit at the terminal A and B, and you can see in this example that I don't have load connected to A and between A and B, which means I don't have to remove anything. I can start right away and calculate the Norton's equivalent circuit. So what I'm going to do is the following. I will calculate the short circuit. So I know I Norton is the I short circuit at the output. So if I come here and I put a piece of wire this way, I need to calculate the I short circuit here. Now, see what's going to happen now after I put this piece of wire right at the output. There will be important changes happening to my circuit, and I want you to pay attention to what I am going to do here. Now, after I put this wire, I shortened the output of my circuit. What's going to happen to that 2 ohm resistor? Hmm. Can somebody tell me what is going to happen to the 2 ohm resistor here after I shortened the output? It will be, that's correct. It will go out of the game, which means there would be no current going into this branch. So in this branch here, I would get zero current, right? And that's why it will be uh, removed from my circuit. Now remember, if I have a zero current, this is going to have a consequence on my other uh, dependent source. Why? If I have zero current going into the 2 ohm resistor, what's going to happen to this Vx? Excellent. So in this case, after I put the short circuit, after putting,
Sure.
yes,
Why is the current for the 2 ohm resistor 0?
because all the current is going to go through the wire. There will be no current going into any other resistor in parallel with a short circuit. And I'll show you why. After putting the wire at the output, there would be no current going through the 2 ohm resistor. Why? Remember, if you have two resistors that are connected in parallel, R1 and R2, the relationship we said R equivalent for those two resistors is R1 times R2 divided by R1 plus R2, right? And this is going to happen. A current basically is going to split into I1 and I2. But what's going to happen if I have R2 being 0? If R2 is being 0, the R equivalent would be 0. Why? Because here I have 0 times whatever is going to give me a 0. So in this case, if R2 is 0, this current I is not going to split into R1. Now this one becomes a 0. Meaning of a 0 for R2, this means that this is going to be a piece of wire, right? Which means if you now try to calculate I2 or I1 using the current division, so now here this is R2 equals 0. That's why it's a piece of wire. Now let's calculate I1. Matthias was asking why there is no current going in I1. Based on the current division, we have learned that I1 equals to I times the other resistor divided by the summation. So the other resistor is R2 divided by the summation R1 plus R2. However, R2 is 0. So this means that I1 is 0. Now let's see I2. What's going to happen to I2? I2 is I times the other resistor in the second branch, which is R1, divided by R1 plus R2. Isn't this the current division that we have learned for two resistors in parallel? Now, if you substitute R2 with 0, you will find that I2 would be the total current. So that's why if you have two resistors or a piece of wire in parallel with a resistor, all the current is going to go into this wire. No current is going to go through the other resistor. So the current I is going to take this path and come back. And no current is going into this resistor. In other words, once there is a piece of wire that is shortening out a component, there will be no current going into that component that was shortened. Okay, okay, that's great. Yeah, okay. Now back to our example here. So now we know this short circuit that I put at the output basically shortened out that component that was in parallel with it. Now shortening out this component means that Vx here equals 0 times 2, 0 volt. So Vx is 0 volt. Now what does Vx equals 0 volts going to reflect on my circuit or affect my circuit? Can you tell me? What is Vx equals to 0 going to do to my circuit?
Creates a wire.
Absolutely. So now I can redraw the circuit. Then I have here my current source, 10 ampere. I have my 6 ohm. Now this is going to be now a piece of wire, as you said, because Vx is 0. And then the, the short circuit here, right? And I short circuit now is, huh? Can you tell me what is the I short circuit? 10 ampere, absolutely. Why? Because we have a resistor here that is connected in parallel with a short circuit. So this 6 ohm resistor is also shortened out by this short circuit. So all the current is going to go this way, zero current is going to go that path because I have two, I have a short circuit connected in parallel with a resistor. So I short circuit is 10 ampere. Okay. So I found the I short circuit. Remember, if I want to, and this is also the I Norton, and this is also the I Norton. Now I can find the R Norton by finding the V open circuit and divided by the I short circuit. So in this case, look what I'm going to do. I will find the voltage at the output here, which is the same as Vx. If you think about it, VOC here as Vx. So just to keep in mind, I can here say that VOC equals to Vx, right? And this is my open circuit. I'm finding the voltage. I am calculating now the voltage at the output of the circuit. Nothing is going to happen. The independent is there. The dependent is there. I will solve it without doing anything to it. I just need to find the V open circuit at the output. The same way I used to do it for Thevenin's when I used to find the V open circuit at the output. So how do I do it? So here we have a circuit, as you can see, that has a current source. So if I can use mesh analysis, and I would be having a super mesh in this case. Also, what I can do, I can use the nodal analysis, and I would be having, for example, a super node as well because of the dependent source here between. If I take this as my reference, then the dependent source is going to be between two nodes that the reference is not one of them. So let's do it this way. So I need this node. So this is my reference. Let me put the color in here just to make it easier for you. So I have a node here. I have a node here, right? And I will call those ones just to just to keep it the same way of coding. I'm gonna call this one V1 and this one V2. I know that V2 is VOC as well, and I know that V2 is Vx, just to keep in mind. So this one is V2, right? But just to, if you want to keep the same kind of format, the way that you used to do it for nodal analysis, V1, V2, V3, that's that way. But keep in mind that VOC is Vx is V2. Now we can write, here we will be having a super node, right? So my super node would be this. So in one equation, I need to write, so super node here, I'll have the first branch is minus 10, it's entering, and then plus V1 over 6. Then I will jump now to the second node within the same equation, and I will continue writing plus V2 over 2, right? That's it. Those are the This is the super node equation. I am done with it. Now I need to find a relationship between my standard variables, V1, V2, and my dependent source. So what do you think the relationship between V1, V2, and my dependent source is? Can you tell me? Please participate. Feel free to participate. the way you want. I mean, making mistakes here is actually an excellent way to avoid making mistakes in the exam. So you can type in, if you don't want to talk, you can type in and I can read your answer. V1 minus V2 is 2Vx. Let's see. Yes, indeed. V1, which is the terminal of the Vx, that is higher than the terminal of the blue one is higher than the red one by 2Vx. This is what is the voltage source is doing. He creates a potential difference such that the one that has the positive symbol is higher than the one that has the negative symbol by whatever this voltage source is generating. As simple as this. So for me, I understand that that V1 is higher than V2 by 2Vx. This is how I understand it as a voltage source. So I have here V1 minus V2 equals to 2Vx. Right?
Sure.
Yes, go ahead.
You're saying these two nodes form a supernode.
That's correct.
Okay.
Notice that the voltage source here is sitting between two nodes that neither is the reference, right? Where's the reference node? That's the reference node. That's the reference node, right? That's the reference node. This is the one that is 0 volt. Okay, so back to our example here. So V1 minus V2 equals to Vx. But guess what? V2 is Vx, right? So I can now substitute this one here and I say, so let me say that this is 1. The supernode is 1. And now I will substitute Vx with V2. So I have here V1 minus V2 equals to 2 V2, or I have, take this one to the other side, it's V1 minus 3V2 equals to 0. So this one is 2. Now from 1, I will condition number 1. I have V1 over 6 plus V2 over 2 equals 10. Now if I multiply by 6, what's going to happen? Now this becomes V1 plus 3V2 equals to 60. So let me call this one 3. Now if I add 2 to 3, I should be able to get rid of the of one variables, which is V2. So 2 plus 3, add them, 2V1, 0 equals to 60, right? Which means that V1 is 30 volts. I need V2, which is the V open circuit. Now, if this is 4, you can say sub 4 and 2. What do you get? You get 30 minus 3V2 equals 0, and V2 is 10 volts. You are right. So V2 is 10 volt. And what's this V2? V2 is VOC, right? So I know now that VOC is 10 volt, which means now if you go back to the previous slide, we said that R Norton is VOC divided by ISC, open circuit, voltage of the open circuit divided by current of the short circuit. So Rn is 10 divided by how much was the short circuit? By 10 ampere. So Rn is 1 ohm, right? So this is how we can solve for Norton's and even Thevenin's. Now, if you look at the Thevenin, if you want to find the Thevenin equivalent circuit for this circuit, you can still find the VOC and find the I short circuit. Then the VOC would be the V Thevenin, right? And the VO and then dividing VOC by the short circuit will give you the R Thevenin. So this is not a big deal. This is also so this is the general approach, which is basically finding the open circuit and finding the short circuit. So the whole
Sure.
circuit gets replaced by 1 ohm resistance. That's correct. So let me. So here now the Norton's is so this is the Norton's equivalent circuit for that circuit that we had earlier in this example. You can also get the Thevenin's equivalent circuit by doing source transformation. So this one can be transformed back and forth even to the following, where V Thevenin would be the V open circuit, which is 10 volt, and this one would be R Thevenin equals to 1 ohm. How did you get this V Thevenin? Well, don't forget that V Thevenin is R Norton times I Norton. Any questions so far? So this is the general approach. We have seen an example where we hooked up a source. That you can still do that. You can still do that. You can use this approach, I short circuit, V open circuit, or you can hook up a source to the output. Knowing the current, you can find the voltage, or knowing the voltage, you can find the current. Absolutely, yeah, yeah. That's the whole point. This is the whole point of those Thevenin's equivalent circuits. As long as you're dealing with linear circuits, then yes, you can replace complex circuits with a very simple circuit that represents that complex circuits. Okay, you can do it the way you want as long as you know what you are doing. Any question about this example? before we move on to the next topic in this lecture. Okay, so the next topic here is finding the maximum power transfer. And what does this mean? In the whole purpose of the circuit is to design a circuit that will transfer a specific amount of power from one element to another. In this case here, if we have a load and this load is hooked up to our circuit, we would always be interested to maximize the amount of power transferred in order to minimize the wasted power or wasted energy. In ideal sources, as we will see later on, we always say that if we have an internal resistance with that circuit, which is basically usually if you look at this circuit, as you can say that this R Thevenin here is the internal resistance for that circuit. And this is my output that I would like to hook up a load to it. So in order to maximize that power that will be delivered to this load, the condition to have a maximum power delivered to the load is to choose the load such that this load is equivalent to R Thevenin. Now, if you look at the relationship for the power delivered to the load, it would be I squared. So this is the I squared times RL, right? This is RL as the resistance of the load. RL is the resistance of the load. So in order to have a maximum power transferred, using the equation P equals to I squared R, where R is the RL, the load, because this is the resistor that I am evaluating the power to be delivered to. Then I is the voltage divided by the total resistance. What's the total resistance? R Thevenin plus the RL squared. So that's the current. Now, if you evaluate this relationship by sweeping the resistance at the load between 0 and infinity, you would get this response. At 0, if RL is 0, then the power delivered would be V Thevenin over R Thevenin plus RL times RL. So if this one is 0, then the power is 0. Now, if RL is infinity, which basically means an open circuit, the power also would be 0. So if you have a short circuit connected to the load, the power would be delivered 0. If you have an open circuit, if you left it as an open circuit, which is an infinite resistance, also the power delivered to the load will be 0. So what is the best load that you can choose for a circuit to have a maximum power transfer received at that load is to pick this RL to be R Thevenin. So R Thevenin, if you choose this RL here to be equivalent to R Thevenin, you have a maximum power transferred to the load. Okay? Any question?
Okay.
Any question about that? Yes, go ahead.
You're saying maximum the power is 0 when the resistance of a load goes to infinity. But there's also an equation for power P equals I squared R. So isn't the higher the resistance mean the more power you get?
But you don't have a current,
Oh, okay, good point.
right? The current would be 0 because it's an open circuit. Does this answer your question?
Oh yes, thank you.
Okay, you're welcome. So if you want to examine this, and I'm not going to go deep into this, but I can give you, direct you to how you to look at it. Take this function and derive it with respect to the load, to the RL, right? Derive it with respect to the RL. Your variable is RL, and calculate the slope. You will find that the slope would be 0 when RL equals to R Thevenin, which means that point. This is the point. When R Thevenin, when RL equals to R Thevenin, you are going to get a slope of 0, which means this is the maximum point for the power. Okay, so now let's go in and see an example how to calculate this maximum power transfer to the load and how to pick this load. Now, this is my circuit. The question says determine the value of RL that will draw maximum power from the rest of the circuit. So we have learned that the value of RL to give you a maximum power transfer to the load should be picked as R Thevenin or R Norton. Doesn't matter. They're the same. That's correct. So the question here is actually asking you to find the R Thevenin for this circuit. So if you think about it, this is what how the question is directing you. So what you need to do is the first thing you need to do is disconnect the load. We've always learned that we need to disconnect the load, put the load aside. So my circuit now is going to look like this. So this is A. I'll call them A and B. And then we have here 3Vx, 4, 1, 2, plus minus Vx, 9 volt. So the question is asking me, in other words, find R Thevenin for that circuit. Well, this circuit has a mix of dependent and independent sources, which means if I want to find R Thevenin, I can go V open circuit, I short circuit, and then find the ratio. This is one of the approaches, right? Or I can hook up a source at the output, switch off the 9 volt, which is an independent, and calculate how much current would be withdrawn from that source. So, in order for me to find R Thevenin or R Norton, I can go V open circuit over I short circuit, right? So, let's start, for example, by calculating the V open circuit. So, V open circuit would be the voltage right at the output here, VOC. So, what do I do? If I take this one, if I want to use, for example, the nodal analysis, and I took this as my reference. Now we're going to talk about the best analyses to use maybe in the future examples, but usually when you have voltage sources connected to the reference, then you don't need to write a nodal analysis here. Why? Because now in this node, the voltage becomes known, right? This is 9 volt. This is 9 volt. So I only need to write the nodal equation right here right? Do I need to write the nodal equation at A? I don't, because there is no current. The current is zero. And this VOC actually is going to result into being here between this and this node, the red node, and this VOC, right? Why? Because there is no current going in here. The current here is zero. And the potential at A would be the same potential at this red node, right? Okay, so let's write this equation. So all those hence are extremely important. Pay attention to, and you need to understand what does a current of zero means for the potential between two nodes. So if I want to write now, I will say that this is my V1. I will write my nodal equation as V1. So V1, it is not zero. It is not zero. Are you talking about the potential? The potential is not zero, but the potential difference is zero. So between V1 and A, the potential difference is zero, if I understood your comment right, correctly. Okay, so let's write this V1, so nodal equation at V1 as the following. So I have V1 minus 9 over 2 plus V1 minus 3Vx over 1. That's it. Equals to 0. Now you have to be careful that you need to find a relationship between this dependent source variable and your standard variable. Why not V1 over 4? Because the potential here at A is the same as the potential at V1. So this is going to be V1 minus V1, right? They are the same potential. Make sense? Remember, we said that the current is zero in this branch. No, 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 no. The potential zero is here at the reference. But why the potential zero at A? Be careful. When I say the current is zero, this doesn't mean that the potential is zero. Now here, the potential at point A, and I will circle those ones with different colors, or I will highlight. The potential here and the potential here is the same. The potential at those two highlighted nodes is the same because there is no current going into the because it's open. No current going into the 4 ohm branch, right? It's an open circuit, which means that the potential difference between potential difference across the resistor R is zero, which means the potential at both terminals are equal. Okay. Now back to here. we said now after we wrote the nodal equation, we need to find the relationship between this variable in the dependent source and my standard variables. What is the standard variables in nodal analysis? What are my standard variables in nodal analysis? Can somebody tell me? No. The standard variables are those node voltages, V1 in this case. Those are the standard variables in my nodal analysis, right? Remember what did we say? We are solving for the voltages in those nodes. So my variables in nodal analysis are the node voltages. So I need to find the relationship between this node voltage and my dependent source controlling parameter. In other words, I need to find a relationship. I need to look in the circuit and see where I can find the relationship between this Vx and V1. Look, I will highlight it again. Look, where's Vx, right? Isn't this the controlling variable for the dependent source? I need to find the relationship between this controlling variable and my standard variable, which is the V node. Absolutely correct. 9 minus V1 is Vx. And this is what I am after. This is my second equation that I need to solve for this problem, which is 9 minus V1 is Vx. Now, if you take this, now if you take the Vx and substitute it here, what do I get? So I will write it here, V1 minus 9 over 2 plus V1 minus 3, 9 minus V1 equals to 0, right? Okay, conditioning this equation by multiplying, or let me first get V1 minus 9 over 2 plus V1 minus 20 minus 21, 27 plus 3V1 equals to 0, right? Minus 27 plus 3V1 equals to 0. Now, if I multiply by, so this is 4V1, so I have here V1 minus 9 over 2 plus 4V1 equals to 27, multiply by 2, I have V1 minus 9 plus 8V1 equals 254, right? Then 9V1 54 plus 9 63, then V1 is 7 volt. Right? So back to here. We found V1 to be 7 volt, which means VOC. Now remember here, VOC is V1. So here on the side, we need not to forget that VOC is V1, right? So this is V1, the one that we were after. We calculated it, and it is VOC. It is VOC. So VOC is 7 volt. Now we need the I short circuit. Okay, so let's go to here, this slide, and now we need to remove this load and put a short circuit. So if I am to now, we need I short circuit. So remove the load and put a wire instead. Then calculate for I short circuit. So here 2, 1, 3Vx, 9 volt, 1, 3Vx, 4, and then come here, put the wire, find I short circuit. Okay. So my reference is here. I will keep it the same. But now guess what's going to happen? Now this is my reference. Zero volt, right? Now if you recall, now A is 0 volt. Now A is 0 volt. So this is the node, the V1, and this node is 9 volt because it is connected between, it is the second, this 9 volt is connected between the reference and this node. So now this becomes a known voltage. I need now to find V. I'm not going to call it. Now this is a different circuit, right? So let me give it a different name so we don't get confused. I'll call this one now V2. Or you can call it V1 prime, whatever you want.
Sure.
I had you explain that.
Yes.
Can you go back to the page or two? I sort of confused as to the steps you took.
Which one? The previous one?
The relationship between V1, Vx, and 9.
Here.
One more.
Here.
Yes. How did you get 9 minus V1 equals Vx?
That's correct.
Because I got V1 minus 2 Vx equals 3.
Because we've been just ignored from that.
You got what?
And the fact
I got V1 minus 2 Vx equals 3.
Where did you get this one from?
Well, you break this up, so V1 over 2 minus 9 over 2 plus V1, so that's 3 over 2 V1 minus 3 Vx.
Hold on a second, Matthias. Here, are you talking about simplifying this equation further?
Yes.
This will.
This is still one equation, two unknowns, Matthias. You cannot solve it. You need number of equations to equal the number of variables. So you still need an additional equation to help you solve for V1 in this
So,
problem. And this is
so
we get it from here by looking at this variable in the dependent source, and we see what is the relationship based on this variable existence in the circuit. Now, if you look here, you will see that this Vx is across the 2 ohm. Do you see the circle that I did?
it's 9 minus V1 equals Vx. Is that a loop equation for this this mesh?
It is an extra equation that will help me solve my problem. So this dependent source will depend on something in my circuit, right? Which is here the voltage across the 2 ohm. I need to make use of this relationship. When I put the node voltages, I found that I assigned V1 to this node, the one in red.
Okay, yeah.
And then based on the existence of this dependent variable in the circuit, I found out that 9 volt minus V1 is Vx, or this Vx indeed is the potential difference between the 9 volt and my node variable V1. Is that clear?
Shouldn't it be free Vx?
So I got 9.
No. Look at the location of the Vx.
Oh, sorry, I was basing it off the other source.
No. You look here. This was already taken care of in the nodal equation. Was in the nodal equation already. You need now to get this variable that is somehow related to other components and make use of it. Otherwise, you would be generating the same equation. It's not going to help you. And that's why we said we look here. Where is this variable in my circuit? It is here across 2. Okay, what can I get out of this variable being across 2? Well, looking at the way I distributed my node voltage, I can see that this Vx is between 9 and V1. Does this make sense?
Yeah, it does now. Thank you.
Okay, great. So let's go back now to here and write the nodal equation. If I am to write the nodal equation here at V1, it would be, sorry, at V2, we don't have V1. At V2, it would be V2 minus 9 over 2 plus V2 minus 3Vx over 1 plus V2 over 4 equals to 0. Why over 4? Because this is now here 0 volt. So I have a potential difference now. Okay? And then what is the second equation? Again, the same. I have Vx from here being 9 minus V2. Now, solving this equation, after substituting, what do I get? Okay, so if you take this one and substitute it here, you get V2 minus 9 over 2 plus V2 minus 3, 9 minus V2 plus V2 over 4 equals to 0. Then V2 minus 9 over 2 plus V2 minus 27 plus 3 V2 plus V2 over 4 equals to 0, right? Then what do we have here? If you multiply by 4, what do we get? We get 2V2 minus 18, right? Because this is 2 plus 4V2 minus 27 times 4 minus 108 plus 12V2 plus V2 equals to 0. And now this is 2, 4, 6, 6 and 12, 18, V2, 19, V2. We have 108 plus 18 equals to 126. Then V2 is 126 divided by 19 equals to 6.63 volts, right? Is this correct? So here 2V2 minus 18 plus 4V2 minus 108 plus 12 V2 plus V2. So we have 2, 6, 18, 19. So V2 is 6.63. Okay, that's good. Now, what is the I short circuit? I short circuit is what? Can you tell me? Can somebody tell me what is the I short circuit? How do I calculate the I short circuit? V2 over 4. Excellent. V2 over 4. So we have I short circuit, which is 6.63 divided by 4, 1.66 ampere, right? So R Thevenin, which is also R Norton, is VOC, which is 7 volt divided by I short circuit, 7 divided by 1.66 is 4.22 ohm. So R Thevenin is 4.22 ohm. So we need to, for maximum power transfer, we need RL to be R Thevenin. RL is 4.22 ohm. And the power would be as V Thevenin. How much is V Thevenin? We said V Thevenin divided by R Thevenin plus RL squared times RL. And in this case, B would be, this is 7 divided by 4.22 plus 4.22 squared. Can somebody calculate this for us? Times 4.22. And the power would be 7 divided by squared times 4.22 is 2.903 watts. Okay, let's see. What is 2.9? I think this is watts, not milliwatts. Right? 7 divided by 8.4.8 0.8 ampere squared 0.6 times 4.22 is 2.9 watt. So it is not milliwatt here. Okay, so power is 2.9 watts. You need to multiply by 4.22. So that's the current. This is the current squared times R Thevenin. Okay. Any question? Any question about this problem?
Can you go back for the last few steps, sir?
Last step.
Last few steps. Sorry.
Okay. Which slide? The one before?
I think 2 or 3 before.
Okay. So what's your question?
So what's the next step after we get the voltage for the open circuit?
The short circuit. We need to find the I short circuit.
So we basically created another circuit to create a short circuit.
Absolutely. It is a completely new circuit. Once you do any physical modification to it, it will be completely new. So the Vx is not the same. Vx here is not the same. I'm always even try to probably distinguish this Vx because now it's different. So you cannot use the Vx from previous circuit. So if you want, you can put a prime here on the Vx. Put a prime, right? A prime, just to show you. And that's why that node, I gave it a different name. I gave it V2. I did not say V1. So then you write nodal equation and you find the I short circuit, and after you find the I short circuit, VOC divided by I short circuit is going to give you the R Thevenin, and this is my R Thevenin 4.22 ohm.
All right. Are you able to post your written notes?
I
For this
do.
problem, I'll have to go back through it.
By the way, I do post all the notes. I do post the PowerPoint, but I noticed that you have to download it. Don't open it in the course link, uh, website. Download it and open it in your computer in order to see all the notes. But all the notes I have done are posted on the course link, but you need to download the PowerPoint file. Don't open the PowerPoint file in the course link. download the PowerPoint file in order to see all the notes.
So if I
Okay?
download it, I'll have your written notes with them.
Absolutely, yes.
Okay. Okay, thank you.
You're welcome. So where did we get this one from? Before you leave, this is gonna be now V Thevenin. This is gonna be R Thevenin, and the load is going to be R Thevenin. So here V Thevenin is the V open circuit, which is the 7 volt. Okay, and then we found the power using this equation. V Thevenin 7 divided by 8.44. This is going to be the current squared times the resistance here of the R Thevenin is going to give you 2.903 watts. So any other questions before we end the session? Okay, thank you so much.
Actually, sir.
Yes.
So to find R Norton or R Thevenin, you have to essentially break a circuit up into two different forms, one of an open circuit and one of a short circuit.
That's correct. This is using the general. This is if you have a dependent and independent sources. But if you have only independent sources, you just need to find the V open circuit for Thevenin and then switch off those independent sources and find R Thevenin by looking at the output, looking from the output. Make sense?
Okay, thank you. But so hold on again. When you have an independent and a dependent source, you need
Then
to
you
break
have
it
to
up.
do open circuit, short circuit. Yes.
Okay.
Make sense?
Yes, thank you.
Okay, you're welcome. Okay, thank you so much and have a good day.